Hi everyone. So this is Ken 422, week number 3, September 8th. Oops. And today we'll be introducing reactor design, and we'll be talking about ideal reactors for a single reaction. And this topic covers chapters 4 and 5 in Levenspiel. The chapters are posted on Blackboard as part of your reading material. Chapter 4 is very short. Chapter 5 is more comprehensive and has all the derivations we'll be talking about. Okay, a bunch of quick announcements. Today, homework two should be due. The homework in which we talked about analyzing data from batch reactors. Solutions have been posted as well. If you can't find the solutions, they're in the week number 2 folder. The homework upload link is also in the week number 2 folder. So just go there and find it. And homework number 3 will be assigned today, and it's due a week from now. Okay, so when talking about reactor design, we need to recognize something. Good reactor design depends on a bunch of things. It depends on your reaction, pathway, and kinetics. However, it's not only a function of the chemistry, it's also a function of your thermochemistry. Your transport phenomena are extremely important, especially your heat transfer, your mass transfer. Mixing requirements are also very important when designing a reactor. So, even though now we're talking about ideal reactors, however, all of these reactors make assumptions about your transport phenomena and about your mix. So when we talk about ideal reactors, there are three main types really. First one is called the ideal batch reactor, and this is what it's usually represented like, or when you have a similar cartoon, similar sketch, they mean an ideal batch reactor. It's basically a vessel with usually have a mixer in it, and there's nothing entering or nothing leaving. Second type of ideal reactor is called a plug flow reactor, and you can see it here. It's just usually represented as a cylinder. And the third type of reactor is a continuous stirred tank reactor, usually CSTR. And here I have feed being mixed and then product being taken online. So there's continuous flow, and it's continuously mixed as well. And the abbreviations used: IBR, PFR, and CSTR. So what are really the differences between these three? So your ideal batch reactor, it's a simple reactor, little supporting equipment. You just have a vessel. I put in the chemicals, I let them react, and then I take my products at the end. It usually operates in unsteady state. We make the assumption that it's perfectly mixed, and by perfectly mixed, we mean that composition everywhere is the same at any time t, right? So time equals 0, time equals, half-life, the end, 5 seconds, 10 seconds. We assume it's perfectly mixed and the composition is the same. It's often used in small multi-purpose plants, for example, specialty chemicals manufacturing facilities, facilities which make active ingredients for pharmaceuticals. They like to use these small batch reactors because you want to make a very specific product with a very specific concentration, and you might want to make another product, whatever, but your procedure is the same. So you have an ideal batch reactor. You need to strip it down, clean it, refill it every batch because it's a batch process. It's not a continuous process. So I can't basically just zip nitrogen through it or something to clean it. I have to, strip it down, take it, disconnect it, clean it, put it back together. And it's also in chemistry and research labs. It is used. It's very widely used. They have these big glass batch reactors. I don't know if you've ever seen it in one of the industrial labs, but it's widely used. Okay, second type of reactor is the plug flow reactor. It's a continuous flow system. It's at steady state. So it's very important to recognize. Steady state for a plug flow reactor. It needs feed and crude product vessels because it's continuous flow. I always need to have feed going in, and I always need to have a vessel to store the products, or move it to another processing unit. So it can't just be a standalone unit where the products exist there. There is no mixing inside the reactor. So the idea of a plug flow, so let's go back to the previous slide. The whole idea of a plug flow is that we assume that the flow inside this cylinder, for example, consists of elements, and all the elements are just pushing each other, right? There is no mixing between the elements. so there is no mixing along the flow direction. So basically, in a plug flow reactor, there's no mixing inside the reactor. So basically, you would have a constant difference in concentration at different points of the reactor and at different times. This is in converse to your ideal batch reactor, where the composition everywhere is the same. Plug flow composition everywhere is not the same. And it's often used in large-scale continuous flow plants, especially oil and gas plants. You find these a lot. It helps you to provide better better operation, especially when you have catalysts and other things. Okay, third type of reactor is continuous stirred tank reactor, commonly referred to as CSTR, might hear as C-star, very common. CFSTR, sometimes they add constant flow stirred tank reactor. Whatever it is, it's this third type. It's a continuous flow system. Sometimes you have only one by itself, sometimes you have a bunch of them in series, which is a common type of method of operation. We're going to talk about reactors in series later on. Usually operated in steady state. Again, similar to a plug flow reactor, because it's a continuous system, you always need to be feeding it product, and you always need to be moving feeding it feed, and taking out product and moving it either to a storage vessel or to the next unit. For this case, for a CSTR, we assume there's perfect mixing. This is implied because of the stirred tank, and it's often used in large-scale continuous flow plants. Okay, so these are the different bullets or the different main points for each of these reactors. So how do we design, or how do we get a performance equation for any of these reactors? So in chemical engineering, any design procedure, and you have to remember this throughout your career, that as a chemical engineer, you need to start from your fundamental equations. And by fundamental equations, we mean two things: mass balance and energy balance. And these will be your starting point for almost any performance equation for a reactor, distillation column, flash column, whatever it is you're using. In chemical engineering, these are the two main principles of design: your mass balance and your energy balance. And your mass balance, basically, there are two types of mass balances. You have an overall balance, and then you have a species balance, right? And an overall balance just accounts for everything. If I have A plus B flowing into a reactor, reacting to give me C plus D, if I put in 5 kilograms, I should get 5 kilograms out, right? This is what a mass balance is. Chemical species, I'm looking at A by itself. So maybe I only put 5 kilograms of A, but because I have a reaction, I get 0 kilograms of A at the end. So chemical species, your in and your out might not be the same because things are happening. However, for an overall balance, whatever mass going in has to leave your reactor, or has to leave your process. And if we look at the small differential element here, so this cube here is a small element of the reactor. So if you think of your reactor, I'm going to chop it up into small pieces and look at just one small piece of my reactor. And in this small piece or element, I have reactants entering, reactants leaving, and within the block, I have reactants accumulating within the element and reactants disappearing by reaction within the element, okay? So thinking about this and recalling what you took in your elementary chemical engineering course, my overall mass balance is usually in is equal to out plus consumption plus accumulation minus consumption, whatever it is. And here I have plus plus because, when reaction engineering, your rate will be a minus, right? So basically, the way I learned it, the way I remember it, is in minus out plus generation minus consumption equals 0. There are many different ways to recall this. And just always remember your mass balance. Let me get this tablet here. Maybe we can write it. Where's my pen? 1 second. Okay, so basically, let me get the pen here. So your overall balance, or in minus out plus generation minus. equals 0, right? This is your overall balance equation. It applies for both mass balance as well as for energy balance. And this will form the basis of all your design procedures. If you want to derive any equation, this is the basis. This is the pillar of chemical engineering right here. Okay. Similarly, the second one is an energy balance, and you see the equation is the same. In is equal to out plus generation minus consumption, and the same idea applies. So heat enters. So if I divide my reactor into small units and I only look at a small element, and when I say I divide my reactor, so let's say you have your plug flow reactor right here. You have feed going in and products coming out, and usually I would divide it into look at a very small element here, and in this element I would have reactants in, reactants leaving, reaction. So some species appear due to reaction, some species disappear due to reaction, whatever it is. However, at the end, similarly, if I have heat in, heat leaving, some heat is generated because this reaction is exothermic, or maybe some heat is being eaten up because this reaction is endothermic. However, the overall balance will always apply. In minus out plus generation minus consumption is equal to 0, right? And this is at steady state. So always remember it's equal to 0 at steady state. However, at unsteady state, this balance changes to, so at steady state, at unsteady state, your balance becomes in minus out plus generation minus consumption is equal to accumulation, right? So this is the unsteady state form of this balance. So again, recalling these design procedures or these design equations, you have your mass balance equation in which in minus out plus generation minus consumption is equal to 0. And this is at steady state. And at an unsteady state, I have in minus out plus generation minus consumption is equal to accumulation, right? And this is at unsteady state. Okay, so please just remember your design equations. It's very important. You must be able to build a mass balance. You're a chemical engineering senior. If you don't know what a mass balance is, or you're unable to at least get 4 out of these 5 elements, then you're in trouble, right? You need to come to office hours and we need to sort it out. But you need to be able to build a mass balance. That's the bottom line. Okay, so taking these design equations into consideration, when we're going to use these design principles to derive the performance equation for the 3 types of reactors we talked about earlier. Okay, so let's start with the ideal batch reactor, which is, if you recall, it's this guy to the left, okay? So taking this ideal batch reactor, we're going to make 2 main assumptions right here. First assumption is that it is isothermal. And the second assumption is that it has a constant density. And if you're going to use the performance equation or you're going to use the ideal batch reactor model, I expect you to write these assumptions at the start of your problem, right? To show me that, or at least to acknowledge that, to acknowledge these assumptions, right? And even, later on, if you want to use these equations, you should always remember that they are under these very specific conditions. So since it's an isothermal reaction, there is no need to make an energy balance because, there's no heat change. Temperature of the feed is equal to the temperature of the product. There is no energy change, so I don't need an energy balance. We just need to note that we must have sufficient heat transfer capability to remove or add heat at the rate that it is released, okay? So because I'm operating it isothermally, if the reaction is highly exothermic, I will need to add a cooler to maintain the reaction temperature fixed. Okay, so now let's look at the mass balance. So what element do we choose for the mass balance? So if you recall from the mass balance, we said we're going to divide the reactor into a bunch of elements, you know, but in your batch reactor, we made a few assumptions, if you remember earlier. It was basically like a closed cooking pot, right? You have this, it's a timer, and then you have a mixer here. We made a few assumptions. One of the most important or the most relevant assumptions in this case is this guy right here, perfectly mixed. We assume that it is perfectly mixed. So this means that whichever all the elements inside this reactor are the same, right? Because it's perfectly mixed. So if all the elements are the same, this means I'm going to choose the entire volume of reactants as my element. So I'm going to perform my mass balance over the entire reactor in one go. And if I write my my mass balance equation, which is N, so this mass balance equation here basically is equal to N is equal to out plus, and disappearance refers to generation minus consumption plus accumulation. And if I look at the batch reactor, there's nothing going in, there's nothing leaving, so these two guys are zero, right? Because the batch reactor just load the reactor, let the reaction happen, and then at the end, I take my product. So there is no input or output happening while the reactor is operating. So let's start writing our mass balance. So now I'm looking for three things. First of all, or maybe two things in this case. So Levenspiel, by lumping generation and consumption, he terms them as disappearance. So it's fine. So let's, we need to find an expression for this term, the disappearance term, and we need to find an expression for the accumulation term right here. So what's the rate of disappearance of species A by reaction? Again, if you recall, minus RAV, which is, you know, your reaction rate, multiplied by the volume, is equal to dNA by dt, right? Do you guys remember this equation? It's from the first slide where we said, you know, first lecture, we said minus RA is equal to 1 over V dNA by dt, or actually minus, right? So if I want to get the change in number of moles, I'm just going to multiply RA by V, and this will be the rate of disappearance or the rate of change of number of moles with time due to reaction, right? Rate of change of moles due to reaction. Okay, sounds good. So we have the expression, we have the term for the disappearance right here. Good, so now we need the term for the accumulation. So let's have a look here. This is a lot of description here. So what's the accumulation of species A? dNA by dt is equal to d by dt Na0 1 minus x minus Na0 dxa by dt. So the accumulation of species A with time is a function of conversion. Okay, so you need to remember this. And so the accumulation of species A, or how much species A remains in my reactor, basically is the initial number of moles multiplied by how the conversion of A. And if you recall, we said that XA is equal to 1 minus NA over NA naught, or CA over CA naught divided by V. So this means that NA is equal to NA naught into 1 minus XA, right? So NA is equal to NA naught into 1 minus XA. So if I take the derivative of this to get the change in number of moles of A, or the accumulation of A, I get dNA is equal to NA naught as a constant, and then I have the minus dXA, which is this expression here, minus NA dXA by dt. And this is the term for the accumulation of species A. So now if I equate, or, you know, if I if you recall from the mass balance on the previous slide, disappearance is equal, sorry, 0 is equal to disappearance plus accumulation. So if I lump these two expressions together by recalling that right here, 0 is equal to disappearance plus, I'm not sure what's going on with this guy today, accumulation. So basically I'm equating these two expressions. So we're saying minus, I'm saying here minus RAV, which is my disappearance, is equal, plus the accumulation, which is minus NA dxa by dt is equal to 0. If I move one of them to one side, in this case, I move the accumulation term, so I get minus RAV is equal to NA0 dxa by dt, and this will be the starting point for me to derive the performance equation. Okay, so if I rearrange it, or if I, put the dt to one side and the dxa to one side, so I get integral from 0 to t of dt is equal to NA0, integral of 0 to xa of dxa over minus RAV. Okay, so now if I, so this then now becomes the performance equation for a batch reactor. Okay, and this equation is very important. You have to remember this equation. You have to know how to use it to perform calculations. We're going to talk about it in a second. But if you're going to take anything out of these slides, or if you just want to a summary of these slides, you need to know how to use the three performance equations we're going to derive: IBR, PFR, CSTR. Okay, and if I look at the plot here, if I plot basically 1 over minus RA versus XA, I can really get some parameters just by plotting. So T over CA naught is the area under the curve, dx over minus RA is a discretization of a piece of the area under the curve. Okay, so how do you use this equation? We need to use this equation, we really need an expression for minus RA. And an expression for minus RA will depend on the type of reaction we're dealing with, right? So if an expression for RA has been determined, then you can use it. So for the first case is if I have a first order irreversible reaction and minus RA is equal to KCA. In this case, I take my ideal batch reactor performance equation, I plug in this expression here, and then I integrate. So in this case, I plugged in KCA instead of minus RA, and I have integral of CA naught to CA of dCA over KCA, and again, this is just equal to minus RA plus this guy minus right here, right? If you integrate, you get minus KT is equal to ln CA over CA naught, or minus KT ln 1 minus XA. And again, this is the same equation we derived during the last lecture when interpreting batch reactor data for a first order reversible reaction. Okay, so this is how you use this equation. And again, I expect you to be able to use it even if I give you a second order reaction. So if I tell you what about the situation where R is equal to K CA squared, you should be able to use it. I just put KCA squared here and I integrate. Well, in this case, I have 1 over CA squared. Hopefully you remember, 1 over CA, so what's the integral of this? Minus 1 over CA, right? If it's KCA cubed, but if it's KCACB, should, write B in terms of A, use conversions, this and that, and you're able to use this equation, right? So with IBRs, there's a bit of math involved, but the starting step is to plug in your rate expression into here. Good. Okay, moving on. Let's move on to a second type of reactor, which is the CSTR. And we're going to derive the performance equation for a CSTR, right? And again, we're going to make a bunch of assumptions here. First one is isothermal. So by saying it's isothermal, we're going to forget about the energy balance. We don't need an energy balance basically because it's isothermal. If you take an advanced kinetics course, or if you go doing a master's degree, or even by experience, you can derive an energy balance. Aspen will do it for you, whatever it is. But ideally, you don't want your reactor to just be running at any temperature. In most cases, reactors are kept running in an isothermal under an isothermal condition, especially when you have or in most industrial reactors, you want to keep a good control of your species, of your thermodynamics. You know, if you have hazardous chemicals, toxic chemicals, high pressures, whatever it is, you want to keep them all under controlled conditions, and this means operating them isothermally. So this is actually a valid assumption, and these equations are quite valid for many applications. Second assumption is constant density. Third assumption, continuous flow. So because it's the CSTR, I have continuous flow. And the fourth assumption we're going to make is that steady state, right? So we're not going to derive the performance equation at unsteady state, but this is at steady state. Okay, so the same thing applies because it's isothermal. We don't need to make an energy balance. And now we need to make a mass balance on this reactor. And again, for the CSTR, similar to the batch reactor, if you recall, the CSTR is this guy. We have feed coming in, and I have products coming out. And one of the most important, or one of the primary assumptions we made, is that it is perfectly mixed. So if it's perfectly mixed, this means that the composition in this part of the reactor is equal to the composition in this part of the reactor is equal to the composition here, everywhere. So all the elements will be the same, basically. So I can perform my mass balance over the entire reactor. So let's do this. I write my mass balance equation. N equals out plus disappearance plus accumulation. Because it's at steady state, accumulation goes to 0, right? Because it's at steady state, the accumulation term goes to 0. And now I have three expressions: in, out, disappearance. Let's start dealing with them. And again, you know, this is your mixed reactor here. These are the notations we typically use. And remember them because we'll use them on the next page. CA note initial concentration, XA note 0, FA note, V note. We really haven't introduced these two guys yet, so we'll talk about these in a second. CAF, this is your final concentration, and we make this very important, these two very important assumptions, where we assume basically that the concentration in the reactor is equal to concentration in the products, right? Similarly for conversion. So these two are very important. CAF equals CA, XAF equals XA. You need to remember this. Concentration in the reactor is equal to the concentration of products. VF, again, this is similar to this expression here. We're going to talk about it in a second. And FA is similar to this expression here. We'll talk about it in a second. Okay. So at this point, I'm going to stop and I'm going to introduce two concepts. The first one is called space-time. Second one is called space velocity. And these are very, very commonly used terms when dealing with continuous reactors. So please, just be aware of them. Reactors. First one is space-time. The unit I use for space-time is tau. And space-time is basically V over small v naught. So V in this case is the volume. And V naught here is, let me just recall this. I don't confuse them here. Give me a second. Okay, so V naught here is volumetric flow rate, right? So, second. Okay, so this is volume, this is volumetric flow rate, and this is in units of volume per hour. And if you do this, basically calculation, find out that the units for space-time is in hours, right? or in seconds. It's units of time. So volume divided by volume per time, could be hours, seconds, whatever it is. You get the space-time. And the definition of space-time, it's the time to process one reactor volume of the feed, right? So if you think about your CSTR in this case, looks like this. I have feed going in, products leaving, and it's mixed. If you're tracing one small molecule or maybe one small block of feed going in, and you want to see how long it takes for it to exit again, the time it takes for it to basically pass through the unit is your space-time, right? So this is the definition of space-time, just be aware of it. And again, you can use either of these equations to get your space-time. So get comfortable or be aware of these equations, know how to manipulate them, because sometimes I would give you, for example, the space-time, the volume, and ask you and then you'll have to determine the CA note, right? And the other term we were talking about, FA note here, it's your molar flow rate. So it's moles per time. This is mole per volume, right? This is volume. So this cancels, this becomes just units of time, okay? So this is the space-time, this is the concept of space-time. These are the equations used for space-time, so take note of it. The second sort of parameter we're gonna introduce is called space velocity. And space velocity is usually denoted as 1 over tau, has units of 1 over time, right? And it's the number of reactor volumes of feed which can be processed in unit time. So it's basically the reverse of this. So if we think about it, if you have a batch reactor here, and I want to find out how much, or how many reactor volumes can I process in 1 second. So if I take a look at 1 second, how many reactor volumes get processed? This is determined using, or the space velocity gives you an indication of this parameter. So again, two terms, space-time, space velocity. Space-time refers to the time it takes to process one reactor volume of the feed, and space velocity refers to the number of reactor volumes on the feed which can be processed per unit time, whatever it is, second or hour, whatever it is. The point for you to extract out of the slide is basically the numerical aspect of it, the equation, and recognizing the variable. So if I tell you the space velocity is this, molar flow rate is this, and a reactor volume this, you should be able to get the CA note, use your kinetic equations, and do your math. Okay. So FA note is the molar flow rate of A into the reactor. So these are some other definitions for you to remember. Has units of mole per second, mole per time, whatever. And this is also an important equation. FA note is equal to CA note multiplied by your volumetric flow rate, right? So FA note, mole flow, this is concentration, this is volumetric flow. Mole flow rate of A out leaving the reactor now is FA note into 1 minus XA. So if you recall, what we're trying to do is trying to get the performance equation for a CSTR, and we need 3 things. We need the input, the output, and the disappearance. So this is what we're doing here. This is your input, right? This is your output, mole flow of A, leaving the reactor, FA0, 1 minus XA, right? The rate of disappearance of A by reaction is just minus RA multiplied by V, similar to what we said previously. So if I combine this, so if I say in is equal to out plus disappearance, I combine them, and now I just do some math. So I lump the FA notes together. FA note 1 minus FA note XA goes to the other side. The FA notes cancel out. I get FA note XA is equal to minus RAV. And this is basically the performance equation for a CSTR, or this, if you can rearrange it to get this expression, or basically V over FA naught, which is equal to tau over CA naught, is equal to XA over minus RA, right? So this is where you need to stop really. The feed is partially converted, of course, but this is a very special case. This is just for your information. So the performance equation for a PFR is right here. You should be able to use it. And again, similarly to a CSTR, once you know your reaction rate equation, plug it in here, becomes the algebraic problem. Alternatively, you can write your CSTR performance equation in this form. Tau is equal to CA naught minus CA over minus RA. And all these, this equation, they're all the same, just rearranging, moving things around, and you'll get them all, okay? So this is your CSTR performance equation. Second important takeaway point from this lecture. Your CSTR performance equation again, so remember them, please. Know where to locate them, and know what each of these variables represents. And if you plot 1 minus RA versus XA, these are the types of plots you get, and you can always, translate an equation, especially a differential equation or integral equation, to area under the curve or slope or whatever you want. Okay. Similarly to a batch reactor, if you have an expression for RA, I can plug it into my performance equation to get basically to solve the problem, right? So for this case, let's look at the CSTR performance equation for a first order irreversible reaction. So for a first order irreversible reaction, minus RA is equal to KCA, which is equal to K, CA naught 1 minus XA, right? So now I'm going to take this minus RA and plug it into the CSTR performance equation. I'm going to substitute it right here. And if I do this, I get V over FA naught is equal to tau over CA naught is equal to XA over K. So basically what I did, I plugged this guy here, and this is what I get, is equal to K CA naught 1 minus XA. And then this becomes the basis to solve your problem, right? So if I ask you, what's the conversion of A when the initial feed is, when the initial feed is, 50 moles per meter cubed, or what's the conversion of A if I double the volume, something like that, you can always use this equation to solve the problem. And of course, you can rearrange it to this form. Tau K is equal to XA over 1 minus XA, CA 0 minus CA over CA. So again, same idea. Your starting point will always be the performance equation. Then you understand your reaction rate, your elementary reaction. You get your reaction rate, plug it in here, you get your performance equation, okay? And, this is a shortcut. This is the CSTR performance equation for first order irreversible reaction. All right, so this ends the CSTR. Now let's move on to the plug flow. So the first two talked about perfectly mixed. Very nice. So now this is the guy which is not mixed, or this is the reactor which is not mixed. So for a plug flow reactor, we're gonna make a bunch of assumptions. Again, similarly, isothermal eliminates our need to write an energy balance. Then we're gonna assume constant density and steady state, similarly to the previous ones. You have the same statement here. So now let's move on to try and write the energy balance for this PFR, right? So which element do we use for a PFR? Okay, if you recall, for your batch reactor and for your CSTR, they were perfectly mixed, right? So because they were perfectly mixed, we just used the entire volume of the reactor for our mass balance. However, for a PFR, there is no mixing, right? We said it's like having a bunch of different elements of liquid just plugging along, right? Pushing each other, and there is no mixing along the flow direction. So which element we're going to choose? We're just going to take a differential slice to this reactor and perform our mass balance on it, right? So the answer is I'm going to take a slice through the reactor because the concentration varies from point to point. So unlike the perfectly mixed reactors where the concentration is the same everywhere. In a PFR, the concentration is not the same. So concentration of the feed versus X, for example, if I plot CA versus X for a PFR, you can see a gradient. So if A is the product and R is the reactant, you will see that there is, the concentration of A drops along the reactor distance, and the concentration of the product increases along the reactor distance. All right, so I'm going to write the mass balance for one differential element, and the mass balance for this element will be input is equal to output plus disappearance equals to, or plus disappearance, and that's it. And the accumulation will be equal to 0 because we assumed steady state, okay? So always remember this, the accumulation is 0 because of steady state. So let's move on and try to have a look at the math. So if I take my plug flow reactor and I take a small element of volume dV, right? And the feed into the reactor is Ca0, Fa0, initial conversion is 0. The feed into this element is Fa, or this is your molar flow rate, right? Mole per time. And the feed leaving this unit is your initial moles coming in plus the change in number of moles, right? It makes sense. And then finally CAF, FAF, whatever it is. So if I take a small element and I want to derive a relationship between this small element and the kinetic parameters happening in this element, especially the change in concentration, the change in conversion. So I want to understand the change in conversion, which is dxa within this small element. Okay, so let's write our mass balance as is. We know our in, we know our out. It's a good starting point. So let's do this. So our input into the small element, and again, talking about a small element of the PFR. So I'm only looking at this guy right here. And this has a volume of dV. And from your previous slide, I have FA coming in, and whatever is leaving is FA plus dF. Okay. So the input is FA, the output is FA plus DFA. Put the A here. Good. The disappearance, again, disappearance will always be the same. However, this time I'm using dV because I'm only looking at this element. Unlike the previous, for a CSTR and for an IBR, our disappearance was represented as minus RA multiplied by V, right? So for the previous two, it was represented as minus RA multiplied by V. For this one, because and this was because we considered the entire volume of the reactor when writing our mass balance. Here, I'm only looking at a small differential element, so my disappearance will be minus RA dV. Okay, so now let's try to combine these, or or actually before combining them, what we're gonna do is we're gonna try to deal with this DFA somehow and change it in terms of XA, right? Because as we said on the previous slide, I want to get an expression for XA. So I write DFA is equal to FA0, 1 minus XA minus FA0 dXA. Same concept to what we did before. If you recall, XA is equal to 1 minus CA over CA naught. It's also equal to 1 minus NA over NA naught, which is equal to 1 minus FA over FA naught, right? These are all valid equations, and you can move from one to the other. So basically, here I'm just changing FA to dXA, which is the term we're interested in. So now, combining these three expressions, I get in, which is FA is equal to out, FA plus DFA, plus my disappearance, which is minus RA dV. Next step, I'm gonna plug in, or basically substitute this equation into this equation to get rid of DFA. So if I do this, I'm gonna get FA dXA is equal to minus RA dV. Right, so basically I substituted this guy right here. So I got FA is equal to FA minus FA0 dxa. FA cancels with FA, and minus FA0 dxa. I move it to the other side. I get FA0 dxa is equal to minus RA dV. Now if I separate the variables, so I move this minus RA here and then move this FA here, I get this expression. dV over FA0 is equal to integral of dxa over minus RA from 0 to xa final and from 0 to V. And this is your performance equation for a PFR. And you need to know this as well. And the application is very similar to the previous ones. Once you know your reaction rate, you plug in substitutes here, you do your integration, etc. Okay. So this is the performance equation. You can always, so if you integrate the left-hand side, because it's easy to integrate, V over FA0, and this is equal to tau over CA0 is equal to integral 0 xaf dxa over minus RA. Alternatively, can move the CA0 here. Tau is equal to CA0 integral 0 to xaf of dxa minus RA. Okay, and this is the PFR performance equation. And this is the third important takeaway from this lecture, right? You need to know your performance equations. You need to recognize how to use them. And for all three of them, the way to use them is through this guy, minus RA. Find out your reaction rate equation, plug it in here, becomes a math problem. Just move things around, algebra, find the right equation, maybe convert from FA note to CA note, whatever it is, solve your problem. All right. And so this is valid for systems of changing densities. If you want to just close it for systems of constant density, then you can always rearrange it and use this expression, right? And they're very similar, but the only difference between this and the previous slide is that now I have an expression in terms of concentration as well. Okay, so if for some reason you don't have enough given to deal with conversion and you want to solve it in terms of concentration, you can use this form of the performance equation. Okay. So again, because with these integral equations, you can always have a look at the area under the curve and get the reaction rate, get some other parameters just from the mathematical artifact of these equations. All right, so now let's, before closing, let's just have a overall look at the equations of two of our reactors, right? So we derived the performance equation for an ideal batch reactor, for a plug flow reactor, and for a CSTR. But when we look at the equations for the ideal batch reactor and the PFR, find out that, you know, they look very similar. They're almost, except that this is time. And this is what? This is space velocity, right? They're very similar equations. So why are these equations so similar? You know, you think that these two reactors are extremely different. We're going to get very different performance equations. Why are they mathematically so similar? You know, this is something you need to think about. So the reasons is that each element of reaction fluid in a PFR actually behaves as a batch reactor, right? So if you think of a PFR here, which is what we have here, because these elements, you can think of it as small elements. So A, B, or maybe C, D, or maybe it's better to call them 1, 2, 3, 4. 1, 2, 3, 4, whatever. And they're all just pushing each other, 5, 6, and all these elements are just pushing each other from inlet to output without actually interacting with each other, right? There is no back mixing. There's no mixing along the flow direction. So each of these units is sort of a standalone batch reactor, right? So each element of reaction fluid is like a little batch reactor that enters at time t0 and leaves at time equals tau, okay? And this is why the conversion in a PFR with space-time tau is the same as in an IBR with a reaction time t equals tau. And this will be important when we talk later about sequencing reactors. Mathematically, you just have to acknowledge or understand this, actually, that you know, because the way a PFR operates, where there's no mixing along the flow direction, each of these small elements actually behaves like a small batch reactor, right? Okay. Then one last point for this lecture, we're going to talk about fractional change in volume of reaction. And this is something important to recognize because, especially for gas phase reactions, you know, if you have a gas phase and you have a change in pressure or a change in temperature, whatever it is, your volume is going to change, right? Unlike a liquid where it's incompressible, there's no change in volume. So for a gas phase reaction, a feed of pure A to start with, and your reactor is at constant pressure. So let's look at this example. I have a gas phase reaction, A goes to B, and the reactor is at constant pressure. I'm going to define this term called the fractional change in volume. I'm using the unit epsilon here, right? And this, the definition of this is the final volume minus the initial volume over the initial volume, okay? And you have to understand that this is very important for gas phase reactions. Because in gas phase reactions, usually change in number of moles corresponds to a change in reactor volume, okay? Because, you know, I could have chlorine or maybe hydrogen and nitrogen coming in, two gases, very large volume, they react, they make ammonia, a gas, the volume decreases. So the mass flow rate is the same, but the volumetric flow rate changed significantly. And this is called fractional change in volume, and you need to note that epsilon, or the fractional change in volume, is defined even for complete reactions. And even if the reaction is reversible, you would have a fractional change of volume, which you need to acknowledge. Let's have a look at a quick example. A goes to NB, but now I have P mole percent inerts. So I have A going to B, but in the process I have some inerts or some impurities which are P mole percent. Okay. So let's consider 100 volumes of feed. P volumes of inert remain as P volumes of inert, right? So if I have 100 volumes of feed, so my feed, let's say, is 100 moles or 100 meter cubed. It's a gas phase, we assume ideal gas, and the concentration of this inert is equal to P percent. So out of these 100, I have P inerts, right? And the 100 minus P volume of A give N times 100 minus P volumes of B, right? So I have, so because my feed is 100 volumes, P of these volumes is inert, 100 minus P is the volume of A, it reacts, and I get basically N multiplied by 100 minus P volumes of B, all right? So if you think about it, I have 100 volumes of feed coming in. However, whatever is coming out is equal to P, which is the volume of inerts, you just zip through, and the volume of B here, which is N multiplied by 100 minus P. If you calculate the fractional change, so if I remember fractional changes, so we call it final volume minus initial volume over initial volume. So I put in my final volume here. This is my final volume minus initial volume over initial volume. And I just do some algebra. This becomes my equation. So my fractional change in volume is equal to N minus 1, 1 minus P over 100. Okay? So in the case when you have inerts, you can directly use this equation to determine your fractional change in volume, where N is your stoichiometry. And again, this is for this type of reaction. If you don't have this type of reaction, you can always count the number of moles. So for example, if I have A plus B will give me 2C plus 1.5D, right? So what's N in this case? N in that case will be, I have 2 moles coming in, I have 3.5 moles coming out. So for every 1 mole of A, I'm gonna get, or for every 1 mole of feed, I'm gonna get 3.5 divided by 2 moles of product, and then your N becomes that number, all right? And you can use this equation directly to calculate your fractional change in volume for cases where you have an inert. So let's recap this idea. In gas phase reactions, we'll always have a fractional change in volume. And the fractional change in volume refers to your final volume minus your initial volume divided by your initial volume. If you know your stoichiometry directly, so if I know that, A goes to 2B, or, 3A goes to 4B, you need to normalize it, of course, with respect to your feed. So for this one, I'm going to normalize it. So I get A goes to 4 over 3B, whatever it is. And this is the N for this case. This is the N for this case. So I just take this N minus 1 divided by 1, and I'm going to get the fractional change in volume. And this is how much my volume changes. So my volume is going to increase by 20% between the feed and the product. Okay. For the case where you have an inert and you know the concentration or the composition of inerts in your feed, you can use this direction. You can use this equation directly. Where again, N is your stoichiometric parameter, and P is the composition of inerts in your feed. All right. So epsilon A, which is your fractional change in conversion, accounts for both the stoichiometry and the presence of inerts. It will also need to account for changes in temperature when we start dealing with non-isothermal situations later on. You can also use the fractional change in conversion to account for changes in both temperature and pressure. And we're going to get to this later on in more details, but basically, so if you have your concentration is Na over V, and if I do some algebra is equal to Na0, 1 minus Xa, divided by V0, 1 plus epsilon A Xa, right? So you need to be aware of this, that, now if I'm looking at concentration, because my volume changes, so I can't just use V here interchangeably. I need to acknowledge that, there's a fractional change in conversion. So I need to account for this parameter. And almost all of your problems will not deal with this fractional change in conversion. It's not a very interesting concept. You just need to acknowledge that when you have a gas phase reaction, your volume is going to change. Okay, this is all you need to know, really. And again, you can always rearrange the equation, do some algebra, and get this expression. Okay, so this is the end of this lecture. Let me go back. The three main important points I need you guys to remember are the performance equations of the three reactors primarily, or the PFR, performance equation. This is very important. The CSTR performance equation, and finally the IBR performance equation, or the ideal batch reactor performance equation. And the way to use any of these performance equations is, first of all, you need to understand your reaction rate. Once you know your reaction rate, we're going to substitute this minus RA expression into the performance equation, and then we separate the variables. So if you're dealing with conversion, you need to separate the conversions to one side and the time, or not the time, conversions to one side, and the rest of them, usually the volume, to the other side. If you're dealing with concentration, you need to separate concentration to one side and the other variables to the other side. And this becomes your performance equation. Then you solve it. If I ask you what's the time at this point, or when time is equal to 5, what's the concentration, etc., you just use the equation as is. Okay, so this is the end of lecture number 3, right? We're in week 3 now. And we're talking about chapters 4 and 5 from Levenspiel. So please, it might be worth it to just have a look at the book chapter. I'm going to post it as well. And if something's not clear, you're having a hard time seeing any of these things, come to office hours. We'll talk about it, or send me an email. Let's set an appointment and let's talk about it in detail. Thank you very much.